Hello, I am Lois from ICRA Robotics, and today I'll be presenting a work on 3D printable liquid metal sensors for delicate manipulation tasks such as coral handling, which has yet to be explored. And so in the past, soft robots have been developed to replicate the physical properties of real-world objects for a number of training applications. These are commonly known as robotic phantoms or physical twins, as they provide interaction feedback in the form of sensing to support both human training and robot learning. And so an example is an abdominal phantom, which is able to simulate different physiological conditions by altering the stiffness of its embedded nodules. And the phantom sensing feedback is then used to train physicians on how you could regulate palpation forces as well as movement of fingers. On the other hand, an example of a physical twin is a sensorized fruit, which can be used as a training object as it replicates the properties of the real fruit, such as ripeness. In the video, these are essentially fake raspberries, which report on pressure or force as they are compressed or pulled from the stem. And this embedded sensing provides interaction data, which is therefore useful for training robotic policies in order to transfer harvesting skills from the lab to the field. And so, inspired by these previous works, we thought that the concept of soft robotic phantoms or physical twins may be useful for problems such as coral farming, which is still primarily done by hand. And so, although our collaborators, such as Charm, are exploring automation, the fragile nature of these corals still make handling quite difficult. We also spoke to Dr. Don Bridge from the Queensland Museum, who manages the Coral Bank, which has a collection of over 40,000 specimens, making it one of the largest in the world. He has discussed with us the challenges of coral processing before they are added to the museum's collection. And here is the following process. The first step involves collecting the sample with a hammer and chisel, then photographing the colony where the sample was collected, and then labeling and tagging the coral. And this, surprisingly, is the challenging part. These corals often vary in shapes and sizes, and hence fastening a little wire with label over it can be quite challenging. Furthermore, corals such as deep sea corals are very fragile. They're prone to being crushed even with the slightest pressure, so you have to be very careful. Furthermore, there are also more rounded corals where fastening a tag might not be so simple because often what happens is that the tag might just slip off from its surface. And hence, this is quite an interesting but yet challenging manipulation problem that we do hope to automate. So once these corals are tagged and transported to the lab, they're then bleached in order to get their skeletons. And these skeletons are then archived and set up in the museum. So manipulating corals are difficult, and this is because they are fragile creatures with very diverse morphologies as shown. Densely branched corals could obscure robotic vision, and it could prevent us from training useful machine learning policies because sometimes contact may just not be visible. And so to solve this problem, we propose sensorizing the object instead. And so in our case, it is the coral. We are proposing soft 3D printed sensorized twins to help us train robots to handle corals safely without actually using real corals and potentially damaging or killing them. We first do this by grabbing the 3D scan of the coral, and then we subsequently design generate the channels throughout its 3D structures. And this coral is then 3D printed. We selected SLA and silicon 40A material. We then subsequently, after 3D printing, we then injected it with liquid metal gallium sand. And this liquid metal gallium sand then reports the deformation the coral is experiencing in terms of resistance. So we measured the performance of the sensing coral in a number of experiments, both benchtop and also submerged, and we have found that we have good stability even after 500 grasping cycles. That's almost 1 hour of continuous experimentation. And overall, the results show excellent response times, repeatability, low hysteresis, including when the sensor is submerged in water. We also measured sensitivity across different branches and used a load cell on the gripper's fingertip as a benchmark. We found that the load cell readings are often quite noisy and non-repeatable, as shown by the large error regions in the plots over there. So, and the reason for this is because with coral structures, because they're spread out and branched, it's very easy for the branches to displace away from the center from the load cell, and because of that, you do not really get very nice contact data. And you may think that, oh, perhaps maybe tactile sensors would be better at measuring this dynamic contact. However, as far as we know, there's currently no waterproof tactile sensors in the market. And the load cell that we are currently using had to be potted to make sure it doesn't get damaged after it's submerged. Again, you may think that vision may solve the problem. However, with densely branched corals, contact may not always be visible. And so this justifies our approach for sensorizing the object instead. And so we also did a mock-up of the coral tagging problem, which involves tying a wire around the sensorized coral. The coral was able to detect the changing tensions of the wire to prevent the robot from over-tightening and potentially damaging the coral sensor. Here are the results, as you can see here, where the changing of tension of the wire could be observed depending if the gripper was moved clockwise or anti-clockwise. And finally, in summary, we hope that the sensorized coral could be used in the future to help equip robots with the skills necessary to perform delicate tasks such as cataloging, digitization, or husbandry. And their output of this work or contributions is mainly in the automated workflow to help autonomously generate complex customizable soft sensing structures from the 3D scan or 3D models, as you have seen earlier. We demonstrated our application of this workflow in the form of a soft sensing physical twin coral, which we then performed numerous experiments on. Finally, we hope that our work would help enable more ethical and scalable coral research, particularly in soft autonomous robotic manipulation, without actually sacrificing any of these corals or the reefs. That is the end of my presentation. I thank you for listening. And if you have any questions, please do not hesitate to send me an email. My email is just down there below. And I hope to see you in RoboSoft next year, which will be based in Brisbane. Thank you.